Hi everyone, welcome back to the channel. In my last video on Boolean algebra, I have covered all key laws except the De Morgan's law. So it's very super important concept, especially for simplifying logic circuits like XOR and XNOR gates. So I am very interested in doing this De Morgan's law because it's a very important concept. So keeping this video short and focused just on that. So let's begin. This is the overall overview of the law that we have discussed in the Boolean algebra. So De Morgan's law is also a part of Boolean algebra. So just two laws that is included in De Morgan's law. So before doing that in Boolean algebra in the previous video, we have AND law, OR law, commutative, associative, distributive, so complement, inversion, identity, absorption. So these laws are very important for the solving of Boolean expressions. So De Morgan's law is also in two expression set so that it helps to us to solve the equations very faster. This is the overall overview of the all expressions that we have seen in Boolean algebra. So last two that is highlighted in purple color, those two are indicated. So those two are the known as De Morgan's law applications or De Morgan's law formulas. So let's begin that. So if you observe the first expression, that is a plus b whole bar is equals to a bar dot b bar. So if you observe clearly, the plus is splitting to dot and the bars are splitting. So if you see the second expression, that is a dot b whole bar is equals to a bar plus b bar. So if you observe, dot is converting to plus and bar is splitting. So you can able to observe that clearly. So let's start with the first expression. The first expression is a plus b whole bar is equals to a bar dot b bar. So in the first expression, so we are going to evaluate with the help of truth tables and circuit diagrams so that you can able to understand very much clear so why these expressions are equal. So if you consider the first circuit diagram equation, so from the equation we can build the circuit symbol. So if you see, that is first one is a plus b, that is OR gate. So we are taking the inversion, that is NOT gate. So a plus b whole bar it becomes. So finally we can simply say that is a NOR gate. So for NOT gate, output will be a plus b whole bar. Okay, we have saw the thing that is the first term, that is a plus b whole bar. So if you split that according to the De Morgan's law, we are going to get this one, that is a bar dot b bar. So we are going to prove that. So for that we have draw the first equation circuit already we have saw. So the second term, that after the is equals to the second term, that is a bar dot b bar, you are going to draw the circuit symbol. So that is AND gate. So in the AND gate you are passing a bar and b bar. So I hope you know the a bar and b bar means the NOT gate inversion. So you can represent like this, that is you are passing a, you are getting output as a bar. So that is with the help of NOT gates. So you are passing b and you are getting output as b bar in the NOT gate. So this representation is same as above representation also. So whatever may be the AND gate, before there is two NOT gates. So this is the very important representation of the AND gate. So these kind of representations can be used in the gate exams or many more important exams like that you can see, because we all know about the NOT gate. So if you add NOT gate before, it will be a bar. So simply we can understand that. So if the circuit given like that, the bubbled AND gate, so it is very confusing. So if you don't know, ever up to now you did not see, suppose if you did not see that one, so you might be confused what is that. So that is known as bubbled AND gate. So in the place of NOT gate, we are going to keep a bubble. So in the b bar also, for the b bar also we are going to keep a bubble. So that is the same circuit as that shown this side. So that is the bubble means that represents the NOT gate. So this is also known as bubbled AND gate. So this is the same representation of this thing, that is a bar dot b bar. So I hope you know how to draw the circuit diagrams. So after drawing the circuit diagrams, so you can able to see the comparison between the first term and the second term and the same circuit diagrams the side before also, that is the NOR gate, and the second one is known as bubbled AND gate. So we have to do comparison between these two. So outputs will be the same or not, that is a plus b whole bar and a bar dot b bar, the outputs would be same or not. So we can be able to compare with the help of the truth table only. So let's see the truth table also. So I hope you can able to see the truth table. So for the simplicity, I have drawn the truth table first itself. So I hope you know how to fill the truth table. So the first two columns are very simple. That is 0, 1, 2, 3 in decimal. So in binary, that is 0, 0, 0, 1, 1, 0, that is 2 2 and 1 1, that is 3. I hope you know how to convert decimal to binary and binary to decimal. So if you don't know, I am giving a video in the description, that is conversion between binary to decimal, decimal to binary. So I after that, a two columns, that is a bar and b bar, just invert. So that is 0 to 1, 0 to 1. So 1 to 0, 1 to 0, that is inversion of a, that is a bar, and inversion of b, that is b bar. So the next column is a bar dot b bar. Just multiply the columns of third column and fourth column, that is a bar dot b bar. So you can able to get the output. So the next column is a plus b. So this is the OR gate, simple representation of OR gate. So you can able to get the outputs. So the first term is 0 0, that is 0. So next all terms would be same as 1, that is as OR gate in outputs. So the last term is a plus b whole bar, that is the XOR output, that is 1 0 0. So you can see, observe very clearly, that is a bar dot b bar and a plus b whole bar are same outputs. So as we can prove that a bar dot b bar, the output of first one, and the output of the second one, that is a plus b whole bar, so both the outputs are same in the truth table, so that we can hence verify that the both circuit diagram outputs would be same, so that we can able to equate the both of the equations, that is a plus b whole bar is equals to a bar dot b bar. So this is the first equation that we have saw. It is a very important. So this vice versa can also be happen, that is the second equation. So let's see that also. So before seeing the second expression, so let's see some of the things that you want to know. So that is the first one that we have already saw up to now, that is a plus b whole bar is equals to a bar dot b bar. So this is the simple two variable things that we can split like that. Dot is splitted into plus, plus is splitted into dot, and bar is splitted. So the same thing can be applied if multiple variables also present. So if you see the second one, that is a plus b plus c whole bar, you can split like that. So again you can split the bars, and then you can convert the dot to plus and plus to dot. So in third term also we have 4 variables. So how many may be the variables? So you can split like that. So dot is splitted into plus, plus is splitted into dot, and the bars are splitted. And if individual bars are separated, then you can come back or trace back also. So the individual bars can also be splitted back, and you can revert back. So if the RHS is given, we can able to write the LHS also. This is the second expression that we are going to see now. So as this is the same of the first one, so just I have replaced plus with the dot and dot with the plus, so splitted the bars. So this becomes our second expression. Only these two expressions are possible. So you can have multiple variables, but expression is these two. So let's start with the same as the first expression only, that we have to consider the first term, the LHS. Then after we would be considering the RHS, we will be going to draw the circuit diagrams, and we will be going to compare the outputs, and finally we are going to compare the truth table outputs. Then we can able to justify, yeah, this expression is true or not. So if you observe clearly, the first term is a dot b whole bar, that is NAND gate. So I am giving in the description, that is logic gates video. Check out those if you don't know about NAND gate. So NAND gate can also be split like that. The first one is AND gate and second one is NOT gate. So that becomes our final output, that is a dot b whole bar. So the second term, the is equals to after term, that is known as RHS. So if you consider the RHS, that is a bar plus b bar, so you are going to draw that one. So as in the first expression we have saw already, that is, so if you pass a bar term, so you are going to have NOT gates before. So a bar is passed, b bar is passed in the OR gate, so we are going to have a sum up there. So as we are passing a two NOT gates, not our inverted output, so we can able to simply represent like that. So as we have see bubbled AND gate, so the same representation can also be saw here, that is bubbled OR gate. So remember this representation, this is very important. Like some of the competitive exams, it's very important. They can ask in MCQs this kind of questions. So not simply direct questions, but they can twist questions. So they might use this kind of representation or representing a bar and b bar, passing b a bar and b bar. So this is known as bubbled OR gate. So if you observe clearly, we have saw the first term, that is NAND gate, and the second term, the RHS, that is bubbled OR gate. So we are going to compare with the both circuit diagrams. So if you see the both circuit diagrams, it looks like that, and the expression, that is if the looks like that there. For this also we are going to compare with the truth table. So with the truth table we can able to compare anything. So just start with the truth table. So we have drawn a two column, that is A and B. So forget about the all things that I have mentioned after that. So first see, observe on A and B. So if you observe, this is a normal common practice that we will be going to do everything in our everyday practice, that is 0 1 2 3 binary representation from 0 to 3. So I hope you know that. So after that you are going to draw A bar and B bar for the output equations. So draw A bar and B bar. So just invert the column of A bar, so that becomes our A. So just invert the column of B, that becomes our column of B bar. So add both of them using OR gate, so that becomes the output of OR gate, that is 1 plus 1, that is 1, 1 plus 0 1, 0 plus 1 1, and last column that becomes 0 plus 0, that is 0. So this is our first output of OR gate, bubbled OR gate, that is A bar plus B bar. So if you observe, you have to take A dot B also, that you know how to take. So this is also a AND gate, simply AND gate output only we can say. So after that take the inversion of A dot B. So or simply I can say that you can take the AND gate or inverse that, or you can simply take the NAND gate output, that is 1110. So just compare those both of them, A bar plus B bar and A dot B whole bar. So you are going to get, I have highlighted in red color also, you are going to get the same output. So that's why we can say, so these two symbols or these two circuit equations or these two expressions are equal. Yeah, I have highlighted there. Let's check that the NAND gate and bubbled OR gate, both outputs would be same. So in the Demorgan's law, this is the second law, so hence proved with the truth table also. So both expressions will be same according to the truth table. So as we also saw in the first expression, so we have saw that it is applicable for the multiple variables also. So in the second in the second expression also, we have A dot B whole bar is equals to A bar plus B bar. So in this also we can have a multiple variables. So you can split dot into plus, plus into dot. So you can able to observe there. So in the second term, red highlighted one, we have three variables. So I have converted dots to plus, plus to dot, and bar is splitted. So same in the green highlighted one, that is involved four variables. So plus is splitted into dot, dot is splitted into plus, and bars are splitted. So you can have the reverse vice versa also. If RHS is given, you can convert into LHS also. So let's have a quick overview. After that we are going to have some examples so that you can able to understand very much clearly. So these two are the highlighted one in the box, that is our final expressions in the De Morgan's law. So these are the things that we are going to have a quick overview. So that is plus is converted into dot, dot is converted into plus, bar is splitted. So if splitted bar is there, we can able to combine also. Let's see some examples, quick examples. So quickly we are going to have 4 examples so that you can able to understand. So after that, try it by your own, these 4 examples also, so you can boost yourself. So the first expression would be A plus B bar, that dot C whole bar. So you can see there. So if you observe there, after the question I have wrote all the steps at a time. So that is as I said before itself. So whole bar is there. You have to split whole bar into separate terms bar. So in between we have a plus operator. So you have to convert plus to dot, and you have to split the bar. In the second step I have done that only. So in the third step, so the second term is a separate term. So you are going to split the second term. So in between we have dot. So dot is converted to plus, and the bar is splitted. So in the third term to fourth term, so we have nothing, that is B double bar. We can able to write simply as B. So this is our final expression, that is A bar dot B plus C whole bar. I hope you understood that example, the first example. So let's also see the second example. So the second example says that is A plus C dot A plus B bar dot A bar plus B bar plus C bar. So again we have whole bar. So we are going to split according to the De Morgan's first and second law. So in this also I have just splitted them directly and wrote full steps directly at a time. So if you know normal algebra or normal math, it is somewhat looking like normal math only, but we have to apply the Boolean algebra. So just first split the whole bar into separate individual terms bar. So I have highlighted with a separate brackets also. So you can split up to bracket wise. So after we have in the first term, that is we have 2 dots highlighted in a red way. So in the second term I am converting the 2 dots into 2 pluses and splitting the bars. So in the third term I have converted all the individual terms to pluses to dots, and individual bar is splitted to individual terms from second expression to the third expression. So I hope you can able to understand. I am doing nothing new here. Just if you understand once the concept here, you can able to do any kind of problem in this way. So just split the dot to plus, plus to dot, bar is splitted to individual terms. If individual terms bar is there, combine both of them if you want reverse thing. So in the last term I have double bars I have removed, the final expression is that. This is one of the most important example. So let's see this example also. In this example we are not going to use De Morgan's law, so we are also going to use the Boolean algebra to solve this example. So let's start. So there have we given that a dot b plus c bar. So after that again we have multiplication, that is a b plus a into c bar. Again we have whole bar. I hope you can see the question. So again after I have wrote the directly two steps, that is a dot, just simply I have written applying the De Morgan's law into the inside term, utmost inside term. So I hope you know how I am splitting, because up to now we have saw two examples. So split the dot into plus, plus to dot, and split the bars. That's it. I have done nothing there. So individual terms. So from the second expression to third expression, so we have individual terms, the dot product. So we have convert dot to plus and plus to dot. So apply a bar to individual terms. That's it. That is our final expression of the third expression. So after that we cannot able to apply the De Morgan's law. So after that we can able to apply the normal Boolean algebra, and we can able to simplify that equation. So for just for directly, if you are doing that with the help of expressions like AND gate, OR gate, so it might take many gates. So after minimizing, let's see how much simple it can be with the help of Boolean algebra. So this is the main use of the Boolean algebra that I can say. So let's see with the help of Boolean algebra simplification. So I have wrote three steps directly there, you can see. So I have multiplied the insert terms, that is a bar plus b bar dot a bar plus c. So you can split the or simply not splitting, just multiply inside terms. So you can get four terms, that is a bar dot a bar plus a bar dot c plus b bar dot a bar plus b bar dot c. So this is just normal multiplication like normal maths only. Just multiply inside terms the two terms. So after multiplying that, you are going to have that. So the first term, that is a bar dot a bar. So you are going to, if I already say in the previous video, that is a bar dot a bar or a dot a or b dot b, that would be the same term, a single term, that is a bar only, the same representation. So the next expression, you can take three, in the three terms we have a bar common, so take a bar common. So you are going to have a bar into 1 plus c plus b bar. So this is the expression. So after taking a bar common, so we have left with the 1 plus c plus b bar. So in the Boolean algebra we have thing that 1 plus something gives you 1. So I have wrote all the things as 1 only. So that is remain final thing as a bar dot 1. So this is a simple application of Boolean algebra. So after that I am going to multiply c bar inside terms. So after multiplying c bar, so you are going to have third term, that is b bar dot c bar, that is output as 0. Because in Boolean algebra only we have property calls anything into its own bar will gives you 0. So after that I am going to multiply a inside. So after multiplying a inside, I am going to get a dot b plus a dot c bar a bar. So in the next term also we are going to have a bar dot a, so that is 0. So finally we are getting a dot b. So if you observe that the first expression after applying only De Morgan's law, it is somewhat big. So after if you applying the Boolean algebra also, so just with the help of AND gate we can able to simplify the much logic into this logic. So this is the one of the main advantage of applying De Morgan's law and Boolean algebra to simplify the or minimization of Boolean expressions. I have mentioned that LHS is equals to RHS, or you can able to do RHS is equals to LHS, both are applicable. So this is the example of if RHS is given, we can able to convert to LHS also. So RHS is just they have given the splitted things, so we can able to combine to form whole bars also. So if you observe, that is a dot b bar plus a bar plus b dot c. So if you observe, in between we have two operands, that is plus and dot. So we have three terms. So we are going to have whole bar, and we are going to change plus with the dot, dot with the plus. That's it. So the second expression is that only I have done nothing new there. I changed plus to dot, dot to plus, and applied a whole bar. So in the individual terms also I have changed dot to plus and plus to dot, and I have applied a whole bar. So that is our final expression. That is our LHS. So if RHS is given. Thanks for watching up to now.